Hello, everyone. It's 11 a.m. here in Colorado. Welcome to the 2023 ACOM seminar series. Thanks for tuning in. It's my pleasure to introduce today's speaker, Professor Rebecca Garland from the University of Pretoria. Dr. Garland received her PhD from the University of Colorado Boulder, focusing on atmospheric science. She was a postdoc fellow at the Max Planck Institute for Chemistry in Mainz, Germany. She was a AAAS Science and Technology Policy Fellow in the Office for Energy Efficiency and Renewable Energy at the U.S. Department of Energy. Before joining the University of Pretoria, Dr. Garland was a principal researcher in a climate and air quality modeling group at the Council for Scientific and Industrial Research, South Africa. She was a coordinating lead author for the Climate and Clean Air Coalition and UNEP Integrated Assessment of Air Pollution and Climate Change in Africa. She is also a founding member of the African Group on Atmospheric Sciences under IGAC. Today, Dr. Garland will be speaking about improving the understanding of atmospheric composition for air quality management in the data-scarce region. Before starting, I would like to mention that you can enter your questions in the space below the video at any time during the talk. And at the end of the talk, I will read those questions. Dr. Garland, please take it away.
Great, thanks, Ching. Thank you for the nice introduction, and thank you for inviting me to present at the seminar series as well. I'm talking to you from a very cold Pretoria, South Africa, so I wish I could be there in nice warm Boulder, but I'm glad that I get a chance to speak tonight or this morning for you all. So as noted in the introduction, I recently moved from the CSIR, so the Council for Scientific and Industrial Research in South Africa, to UP. And so I'll show results from both groups, and that's also why you can see on my title slide, I've included Magesh Naidu, who's now leading the air quality work at the CSIR, because a lot of the CSIR work is what we've worked on together. For both of these groups, we work on a range of air quality issues with a focus on South Africa. And a lot of our work is to improve the evidence base for policymakers. A lot of our work, really has to show the impact and inform decision makers. That said, we do have data scarcity, and that does impact on our database and our evidence base as well. So today, I just wanted to highlight some of the approaches and some of the findings of our work in trying to work within these gaps in data, and also to highlight some of what I think are the really interesting atmospheric chemistry questions of our region that are still outstanding. Okay, so I think as scientists or in data scarce regions, but even outside of data scarce regions, this tug of war happens quite a lot, sometimes in our own heads, right? That like, no, we need more information, or modelers want to do one more run, or experimentalists want to do one more experiment. And on the other side, like, we just need to make a decision, or we just need to write that paper. And I see this very often between scientists and policymakers. And when we live in a data scarce region, I mean, we never, nobody ever has all the data that they want. But when we're in a data scarce region, we really don't have all of the data that we want. So it's very easy to just get stymied and not do anything, thinking we don't have perfect data. So we really can't do anything. But of course, we do have some information. And so a lot of what we think of is, what do we know, what don't we know, and what conclusions can we make, which is very common science policy linkages as well. And so this is just some of these pictures, and I'll show some of these again. There is a lot of information that is out there. But when we don't have a lot of data, we also often take an integrated approach, because we need to use bits and pieces that we find from different sources. And this takes a lot of collaboration. So the focus for today, what I'd like to talk about is, like I said, some of the work. And a lot of this focuses on integrated work, using different approaches, different data sets, trying to combine them together and assess the available information, see how we can improve it, and test really if it's good enough for the evidence base to make decisions. We do have to be highly collaborative in this. We are a very small group here at UP and similar at the CSIR. And so, we're not experts at everything. And so we collaborate quite often. Not only expertise across atmospheric science, but then also, with public health, with impacts people as well. And with that, you'll see on the slides, I have the logos for the collaborators and the funders on the slides as well. So I won't have a separate acknowledgements because I'm kind of showing highlights from a few different projects. And as I noted, a lot of this work is while I was at the CSIR, so you'll see that logo come up a lot as well. I'm going to focus first on South Africa. Then I'll talk a bit about the African assessment as well. I know that there's initiative within NCAR to start to look at African atmospheric science and atmospheric chemistry. And I think the results from the assessment that will be out soon would really help in that initiative. And also talk to some of the atmospheric chemistry gaps. The picture that I have on the right is, some of the integrated approaches that we've taken. I put emissions in gray because to me, emissions really are where it all starts. And we've done a lot of work on trying to improve emissions. But before I go, I just wanted to give a brief introduction into air pollution in South Africa in particular. So very often when we talk about Southern Africa, the first thing many people think about is biomass burning. I might say felt fires sometimes as well. That's the same thing. That's just grass fires. So biomass burnings, in our region, fire is a very important part of the ecosystem. And so if we look at the emissions, which is what this figure is showing, we know Southern Africa has a lot of emissions from biomass burning. And then what the animation is showing kind of quickly, but still it's simulated aerosol optical depth from a climate model. It's just showing the multi-year average per month. And you can see as we get into our spring, so your fall, as we get into the austral spring around August, September, Southern Africa is when our aerosol optical depth is the highest. However, in South Africa, and particularly in urban areas, our ground level particulate matter do not have the same seasonal cycle as AOD. And I'll show on the next couple slides down that PM actually peaks in our winter instead of our spring. And so this highlights some of the complexity and differences between air quality and really the atmospheric chemistry when we think of the full column. There's been lots of campaigns on biomass burning. There's still many unanswered questions. It's obviously very complex. And part of that is because really, how widespread it is. And then the interactions that comes with it with other sources as well. I hope this picture is coming up okay. This is monthly averages from tropomi of NO2 for February and then August, so our winter into our spring. When the biomass burning, you can see the NO2 is bigger here over kind of the central southern. As the season goes on, the burning goes more south. But this whole area in August is a lot more orange. That's what I hope is coming through on everybody's screen. And it's much whiter here in February. So even though not just in these intense places, but across Southern Africa. These guys that you see on your right-hand side, this is actually our cities and our coal-fired power stations and another city, Cape Town, down here as well. So we have strong interactions between the natural and anthropogenic emissions. I'm not going to talk very much about biomass burning, but I did want to start there first because it's one of the main sources that we think about, particularly driving a lot of atmospheric chemistry during our spring. But also to note that it's, it's an important natural source, but it's really only one of our sources. And I say this, I use this slide a lot and these words a lot when I describe South African air pollution. That we have a wide variety of natural and anthropogenic emissions. And where I am, which is on the high veld, I'll show a map just now, really unfortunate meteorology. We have very stagnant and really recirculating air masses across our winter when we have even increases in emissions. And so just going through, I've took lots of pictures of different types of sources that we have in South Africa. This is the biomass burning in a more up-close picture, biogenic as well, community-based sources, particularly in low-income areas that don't have access, for example, to electricity for cooking and heating, or trash burning as well. In the big cities, we have a lot of traffic. This is sitting also in the area that we study, and this is NOx emissions from lightning. And then we have our large industrial regions, which Trobomi can make beautiful pictures of, beautiful measurements of our coal-fired power stations. And I'll show those in just a little bit as well. But the area that I'll speak to mostly is Gauteng province and surrounding. And so that's actually where I'm talking to you from today. I'm sitting here in Pretoria. Gauteng province is this little guy. The cities of Pretoria, Johannesburg, and Ekurhuleni sit within Gauteng province. There's about 15 million of us, probably getting towards 16 million of us now. We have quite poor air pollution. And that's often driven by particulate matter and ozone. And they often exceed our national standards. So that's what NAQUIS is, our national ambient air quality standards. We've seen some improvements in pollutants, but really not enough. We also have really highly spatially heterogeneous emissions, sources, concentrations, as well as vulnerability. So not just our air quality, but also the impacts. And that can be seen here in this picture at the bottom. If you can see these houses in the front, this is a low-income residential area called Alexandra. There's also some informal setting in here, so really shacks. And then what you can see in the distance, which is very close, as you can see, is Sandton. And Sandton has been labeled the richest square mile in Africa. So over a very short distance, we have really large differences in socioeconomic status, but also vulnerability as well. We also know that we have air inequality, to put it simply, that the highest PM where we have measurements are in low-income areas. That's shown in this Hershey paper that did an analysis of historical particulate matter concentrations. If you look across our seasons, and then our winter, remembers in the middle here. So in a low-income area, this is PM10 for a low-income area that will have domestic burning. So that's who will use coal or wood for heating or for cooking, have a much higher PM10 than measurements that happen in an urban or suburban, or even in the red in an industrial. The gray then also shows the PM 2.5 for domestic burning. So as I noted earlier, our AOD, it peaks more in our spring, so more August towards September, but our ground level, really driven by meteorology and increases in emissions, peak in the winter, and particularly in low-income areas. Just zooming out a little, so when I talk about different areas in South Africa, you know where I'm speaking about at least. This here is Gauteng province, so what I was just showing. We have 3 air quality priority areas that surround us. So these are areas, if they're priority areas, they have poor air pollution and specific management challenges. The 3 cities of Tshwane, Johannesburg, and Ekurhuleni, which sit within Gauteng. And then if we look outside, just a little bit, all of these black triangles are our coal-fired power stations. So our coal-fired power stations sit mostly to the east of Gauteng. There's also one down here right to the south. And then if you look on Tropomi, you'll always see 2 other little dots kind of up farther, and they sit a little bit farther from Gauteng, up here in the Waterberg. I'll also very often call this area the industrial Highveld, so either talking about Gauteng or the Highveld. The Highveld means just that, we sit on a high plateau. So we are about a mile or so above sea level. And we have, as you can imagine, with a city and a large industrial area next to it, it's a very complex management problem. We have local pollution and also regional, such as the biomass burning. When we talk about this area, one of the things that comes up very often is that we are also one of the NO2 hotspots. If you look in the satellite, South Africa, you can see that. You can see that just in the Tropomi images that I showed of Africa. This is some work that was done with OMI a while back in the Duncan paper. looking at the hotspot that goes over both Gauteng, but also in Mpumalanga, and then looking at the trends as well. And so we have different sources that make this hotspot, some of them at the ground, such as the urban, but then also some of the industrial. And our coal-fired power stations have very tall stacks. We have very tall stacks because we have this very stagnant atmosphere in the winter. So we want to ensure good dispersion of them even in the winter. But that means that our NO2 from these is really emitted quite high up. So now our group, this was more historical work. Our group is continuing working with this with a collaboration with University College London and a PhD student now using tropomi measurements to look not only at the hotspot and also different trace gases, but also looking into emissions as well. And as I said in my title, so just some background, I hope now we have a little we know where things are in South Africa when I start to bring up the different areas. We do have data scarcity. We don't have zero data, but we don't have all of the data generally we would like or that we would need. So we are lucky, we do have regulatory monitoring stations. We have about 130 of them across the country. What you can see here in Gauteng, all of these dots are stations that should measure PM 2.5. However, we have really different and varying levels of data capture and data quality, which is kind of what this color scale is showing. The ones in black between 2015 and 2019 had zero data, actually, even though they were supposed to be measuring PM 2.5. So in the end, we only have a handful of stations that have a really good long-term record, which then also limits what we can understand because unfortunately, the well-maintained stations tend to be close together because it's the same network. However, atmospheric, air quality data are not the only data scarcity. We only have compliance monitoring really, so we only have the masses of our criteria pollutants, which are similar criteria pollutants as in the US or Europe. So PM, ozone, NOx, SO2. And CO as well some places. But we also have a lot of uncertainties, for example, in our health outcomes, also in our emissions as well, both natural and then also some of these really small community-based sources. If, for example, if waste burning only happens when the waste isn't collected, and if it happens different places around a community, that's very difficult to model, right? You want something that's a little bit more regular than that. And there's a lot of, while we do have regulated sources, a lot of them, we still do have non-regulated sources. And very interesting, the last study that I'll show today is when we did some work with GAINS, with an integrated assessment model, looking at scenarios into the future and using different mitigation scenarios. And what we found is for industries, even for industries that are reporting, we couldn't get information out about what controls are already in place because that was considered commercially sensitive. So we could, in this analysis, be saying, hey, industry X, you need to do mitigation measures, this. They may have already done them, and we don't necessarily know. So that was also another type of data scarcity. And then just last, and I don't want to be too negative past this, I'm not going to be very negative, but also what we noted was we didn't have quantified future scenarios. So for example, for the GHGs, we have future stated pathways. We do have our commitments to the UNFCCC, nationally determined contributions. We've mapped this out, but we don't have the same thing with air quality. But we do, of course, have a goal, and the goal is to be in compliance with our standards. So yeah, I'm gonna stop being negative, move on. We don't have all the data that we need, but our group and all of the groups in South Africa are working to try to improve this evidence base to support improving air quality. So now I'm just going to show some of the examples of some of the work that we've been doing to improve the evidence base, and then finish up talking about a very specific policy linkage, a very specific project that focused on the linkages to policy. And with this, we worked across the emissions pathway. I'll talk a little bit about emissions. Not so much about transport and transformation, but with simulations, we take that into account and investigate, and then to the ambient concentrations. So just to note, I'll show throughout the kind of these different results some simulated some simulated ambient concentrations. These were all done with the CSIR platform. So the CSIR air quality modeling platform, it's really the only chemical transport model set up in South Africa. And it's used regularly for research and for supporting policy. The CTM used as CAMEX. It can either use WRF for historical runs, or the CSIR also runs a climate model from the CSIRO in Australia, the CCAM climate model. So both historical and future climate runs are possible. I'll only show historical runs. So now thinking along the impact pathway. So just to highlight some of the work that we've been able to do even within this data scarcity. And as I noted my first slide, the little gray guy was emissions, because I said he's very important. And so we spent a lot of time improving emissions. Before any modeling study could start, we would work on developing high resolution local emission inventories, both for management, as I'm showing here, and on the next slide, I'll show for modeling as well. So for management, generally what this would be is trying to develop something that looks like this figure here. This is for Gauteng. Per pollutant, the different colors are the different sources. And this is helpful for management to start to see where, right, are the main sources. As probably would be expected when you look across these pollutants, doesn't matter really what the different sources are at the bottom, but we see the colors are all different, right? As we know, agriculture contributes to NH3, SO2, a lot of it is the airports and the industry. We have different sectors across our different pollutants, and that's helpful to show to management. And one of the key aspects that we worked hard on is trying to get as many sources as possible, because before, a lot of the focus was on industrial emissions. And I think that's where it starts very often. They're easier to capture in some ways. But if you only try to work on like industrial and say traffic emissions, all of your policy will also only focus on industry and traffic emissions, and not all of the other sources as well. And we have very complex community-based sources, as I noted before, with domestic burning and waste burning, which are linked to poverty as well. So this is very difficult also, how to have interventions to support and to change those emissions, because it's really the drivers of it are poverty. But with that, the reason for developing the emission inventories was for modeling. And so for modeling, we need the spatial and temporal resolution. And we've also, when we develop these, then try to compare to the globally available emission inventories as well, because of course they're available and they cover South Africa. This isn't Gauteng, this is Durban. So this is the Indian Ocean here, but it's just such a pretty picture. I like to use this one because this is transport emissions. So this is transport emissions, it's NOx, the total for the year. You can see in HTAP, right, the coarser resolution, you at least get where some of the hotspots are. But now with just more local information, which a lot of places would have at least some of this, we could get down to where you could start to even see the road. And I just wanted to highlight this. I think it really shows, pictorially what one can do with local information. You can at least get some spatial diversity or some of this variability that would be in these urban areas. You can see the domain totals are very different. And, that's still work, like which one is closer? There's a lot of work on that. But at least the spatial resolution starts to get a little bit better. And that's something I just wanted to note, that it's not that the IGAC Gaio African Working Group is really working hard on this to get and improve emission inventories with local information across Africa. And so working on emissions has greatly improved the modeling that we've done, both in increasing sources and also trying to get higher resolution and improving data. We're now also trying to use satellite measurements for top-down emissions of trace gases. Like, as you can see, this sometimes can be quite different, but we also don't really generally have local emission factors. So that's also another gap that adds into some of our uncertainty. Moving on to ambient as well, and some of our findings from there is we generally see really large regional scale of secondary pollutants. And being secondary pollutants, perhaps that's not terribly surprising, but very often for policymakers, the large scale is a little bit of a wake up. And so what I'm showing here, just the only color really that's important is red. And so what I'm showing here is PM 2.5 on the left-hand side, ozone on the right-hand side. This is 24-hour average of PM 2.5. Johannesburg is here. This is now an area just to the south of Johannesburg, one of our priority areas. And you can see the ring road. This is where Johannesburg is. The red means, excuse me, that it's out of compliance. So you can see for like PM 2.5, most of the area is red. For ozone, we can see the area is red, right? So we just have this large scale, really regional and secondary pollutants, which we know are also much harder for management as well. The one thing is that all we have to compare this with are a couple stations that have PM mass, and then a few ozone stations, but the ozone stations are in green, and they're all in industrial areas and where people are, which makes sense as we're trying to protect health. The circle here, if you've noticed that, the one area that's not red, well, that's our coal-fired power station. So it's actually titrating out right around the ozone. And the industry did, luckily, just with a laugh, say, oh, so we're actually cleaning the air I see from this. But if I take away, I told them no, of course. If we change now the scale, so here we just made red the exceedances. Now, if I make this a more natural scale for ozone, you can start to see, where we have these real peaks. So a lot of the people live up here, live down here. Where this red is starting to go is getting into farmland and getting where there aren't people. And also, the regulatory agencies will put monitoring sites where there's people. We don't really have any ozone monitoring in any receptor sites. And this is one of the key things, I think, for chemistry that we need to start to think of. I'll unpack each of these in the next slide just to show other results that also highlights the complexity of PM and ozone. And first is to start with a different study that now used machine learning. So this is a machine learning model that was a project led by Emory together with us, where it used a whole bunch of different information, and AUD was a really important factor in it, but it was able to develop the seasonality that followed the ground-based measurements. So it's machine learning trying to get at PM 2.5 ground level. And what this is showing, once again, this circle here is where Johannesburg is, and the white, I hope it comes out, is Gauteng. Across our spring, summer, winter, and fall, the higher concentrations are in orange. And so when I first saw this, I know PM 2.5 is a regional issue, but this is really large. My first point was, whoa, is our PM problem really that widespread? That's not what we see in CTMs. But we also, outside of Gauteng, we don't have measurements out here, so we don't really know about that. And also, we don't have compositional measurements to see if our models are getting it right or wrong for the right or wrong reasons as well. So with this, we are starting to put out more low-cost sensors to kind of develop some hybrid networks to see at least the spatial distribution of some of these more regional pollutants, well, PM 2.5 at least. And then for ozone, if I was thinking when I put this in, that if I wanted to make a presentation about where we have lots of gaps, I would focus on ozone. The thing is that I mostly focus in my research on aerosols, but just because the ozone problem is so large, I've really started to think more and more about trace gases. And this is a paper that we just came out that was an historical analysis of ozone in the city of Johannesburg. This paper was by Nadine Boudoir-Dedekind at the University of British Columbia. And she looked at data when she was a postdoc with us in the city of Johannesburg, looking first at the exceedances of ozone per year. So this is shown in the top graph. We have the number of ozone exceedances at 3 sites in the city of Johannesburg and how many exceedances were allowed. So just to note, unlike the US, if in South Africa, if 12 o'clock, 1 o'clock, 2 o'clock, you exceed your standard, that's 3 exceedances per day. So you can have more exceedances than you do days. And so the blue site is where we have a lot, it's an intersection of major highways. So we don't always see exceedances there, but the green is one of the suburban areas that's quite far from the large highways. And we see a lot of exceedances. You can see up to 478. However, we have to note that this is a conservative estimate because what these lines are showing is the percent data completeness. So for example, this green here, so in 2007, Delta Park, that is that suburban site that have over 200 exceedances, but we only had about 70% of the data for that as well. So we do know that ozone is a large problem and it's a widespread problem. Our modeling showed us that as well. It is difficult to assess the chemistry of it. We have NOx measurements, but we don't really have VOC measurements. When we tried to, Nadine did a lot of work trying to figure out what she could say about the chemistry. It was really the only thing we had, and at one site only was CO measurements. We have a very strong seasonal cycle. Our ozone on the ground peaks in spring. But we have really complex drivers. We have lots of sun always. We have very seasonal, also strong seasonal cycle in meteorology and changing emissions, biomass burning in our winter into our spring, but then also across the year. And then one of the really interesting things she found is she was able to look at water vapor. And from water vapor, she estimated the production of HOX, and so then the impact on the production of ozone as well. And what she saw is that we look at here where ozone is in red, so we see an increase in our spring. The spring is shown here in green, so you can see how ozone peaks in spring. And then when we have winter data, for example, it's much lower. The black is the production of HOX estimated from H2O. And so it seems to be happening, and this is really, the first time we looked at this and was only one site that had the data where we could look at it, is in our winters, we have lots of sunlight, we have NOx, we do have some VOCs, but we don't have much water vapor at all. It's extremely dry, which is why I continue to cough currently. But then once our rains start to come in the spring and the water starts to increase, we also see an increase in ozone. So this suggests a really important role for water. There's many open questions on this. And one of the things, I think particularly for this seminar, I'd be interested to discuss is, how to address some of these more complex atmospheric chemistry questions with data scarcity as well. And that's one of the things we're thinking about now. Excuse me. So just to bring together these last these slides before I then go on to show an example of some other work that we built upon this foundation for impacts into policy. Is that, so a lot of our work, we continually are trying to build the evidence base. And it's a small community here, we're a small group, working together, we're trying to slowly build the evidence base so that we can support policy and we can improve our air quality. A lot of this, and as I've shown, we've been working on characterizing our urban pollution. PM is a strong focus, but there's very little information more than mass. I've listed here, there have been other groups have done some source apportionment. There are some Spartan instruments. There is some pollen measurements, which is an interesting aspect in PM, particularly I think when you sit within a NOx hotspot and ozone everywhere, there could be a lot of interesting things. And right now we are working a bit on testing hybrid networks for reference grade and lower cost sensors to try to understand the spatial distribution as well. And really trace gases are often forgotten. We have measurements in South Africa of trace gases, but across a lot of the continent there aren't. There's PM, and that really is it as well. And so we're also been working a lot on emissions, as I noted, and then using satellite measurements for emissions. So what I'd like to talk about really to show this link of how we've built upon this evidence-based and the modeling that we've used to improve air quality management is using reduced complexity models. So I like this quote of my collaborator, Peter Adams at CMU. We want low-cost models as well as low-cost sensors. And so RCMs in some ways can be thought of as low-cost models. And just really quickly for people who aren't familiar with the reduced complexity model, instead of saying you have your emission inventory, you run your complex air quality model, you change your emissions, you run your complex model, and that's how you get different scenarios. Instead, you develop a statistical relationship between changes in emissions, changes in concentrations. And this really works for PM 2.5. Something like ozone is much more complex, and it's really the focus of RCMs on PM 2.5. So you develop a statistical relationship between changing emissions and changing concentrations of PM 2.5. So on the fly, you can do different policy analyses and then look at the changes and impacts. There's many different forms of RCMs. The project I'll show, we used GAINS. Also, the African assessment used LEAP. It didn't use the IPC, which is the RCM part of it, actually. We have had a training in South Africa about RCMs, and we're continuing to test, similar to what I showed with some of the earlier work of, how much information do we need to make a decision? It's also how complex of a model do we need? Because a model such as GAINS, which I'll show some results just now, it is informed by a complex CTM. So there's a lot of CTM results that to develop this statistical relationship. But could this be done even simpler? Sorry, I'll just skip that so I can cover the rest of the stuff. So I'll highlight here is a project that we finished up for the World Bank. There was a collaboration with the institutions you can see here. And with this, what we did is we wanted to have really quantitative scenario assessments to support air quality management. And very often, we had evidence-based. I've shown you some of the evidence-based that, we had before this project, but we really built upon that because before what we would do is really look at, okay, you have some activities, you get your emissions, the PM 2.5 exposure, generally through a complex CTM, the CSIR model, and health impacts. What we hadn't done is kind of close that loop. And that's what we were able to do by using the GAINS model, is close the loop using an integrated assessment model, a reduced complexity model, to now be able to, on the fly, look at multiple different policy scenarios and also set targets as well. We are still waiting on the final stakeholder engagement, so these results are considered preliminary still. So for our integrated modeling, we focused on, as I have written 4 times here, trying to use as much local data as we could, because GAINS, which is the Greenhouse Gas Air Pollution Interface and Synergies model from IASA in Austria, GAINS is global. Like other global models, South Africa is already in there. So really what we did is we tried to improve it. What I'll show is a little bit of emissions. In the emissions, we look across species, but for ambient concentrations, it's only PM 2.5. This is another example of emissions. I can never get tired of showing emissions. So this is just domestic fuel emissions for Gauteng for the 3 cities. So Tshwane or Pretoria, where I'm sitting, Johannesburg, and Ekurhuleni. So the very first scenario that we looked at, and that for science I thought was really interesting, was a counterfactual. So the question was, what would have happened if we hadn't had any air quality management? So South Africa has air quality management policies, but this was saying, if nothing happened since 2005, what would air quality have looked like? So a completely made up scenario, but still. So what I'm showing is an emission space for NOx, PM 2.5, and SO2. The baseline is on the left-hand side, and the no further controls is on the right. And just to note, the models in 5-year increments. So this is 2020, but it's not a COVID 2020. We actually use 2019. So don't think COVID when you see this 2020. So what we see is that if we hadn't had any management since 2005, we would have had much higher emissions across all of these. And if we look at ambient as well, we have baseline PM 2.5. And if we hadn't done anything, we have much higher PM 2.5 levels. And so while we're still not in compliance, this simulation at least says we're better off than where we were. This, I hope, gets some traction because we have had a recent constitutional court case where our right to clean air was upheld. So in South Africa, it's a constitutional right to have clean air. And this was upheld as well, that this area, Gauteng, but also the Highvelds, the pollution isn't getting good enough, fast enough. But at least it seems maybe we're better off than where we were. But we're not where we need to be. And that's really the key point. And so this was an optimization scenario that we hadn't been able to do before this project, where if we look in 2020, so where we are now, we look in 2030, the end year, so now looking forward, And if we say, okay, if we just continue where we are, we'll move and we'll increase emissions. This is emissions of PM 2.5. We'll increase it a little bit. But where we want to go, if you can see, is all the way down here. This is the optimized target for 20 micrograms per meter cubed, which is our current standard for this. This is a large decrease in emissions. It's a large decrease. Also, the different colors are just different sources. So it's a large decrease across lots of sources. And this was actually quite surprising to policymakers. Just we hadn't, this is again highlighting the large structural changes really one needs of energy use in order to get to our air quality goals. We hadn't been really considering such large emission decreases before. And if we have these in 2030, what it would look like, and then obviously it will get much better as well. I'll just continue on with this. And then also this is one of the final figures from that assessment. So, providing the different information on the sources of the PM 2.5, but also where it's coming from. And so what this shows here is the kind of the average PM 2.5 for Gauteng. So you take the average where it came from. About 5 micrograms per meter cubed are natural. Natural in quotes. There's also some uncertainty in here. But if you remember, the new WHO guideline is 5 micrograms per meter cubed. So even if there is tons of uncertainty in this, but even though with that, we still see that with no people in this area, we would be above, or at least close to 5 micrograms per meter cubed. Outside of the province gets us over 10, and then the rest of the pollution sits within Gauteng and across different sources. This 10 is quite important because currently our standard is 20, but in 2030, it'll be 15, which, that doesn't leave much space between natural and outside Gauteng. For Gauteng, which by 2030, we already are at almost 16 million, we're going to have a lot more people. There's a lot of uncertainties in this. We don't have a lot of information, is this source profile right? We only had a few stations to validate against. But again, even if we have uncertainties, this is showing the large amount of work that has to happen in order to improve air quality. And I'm getting to the end. I just wanted to highlight some of the findings from the Integrated Assessment for Air Pollution and Climate Change. Just really to highlight that this is out there and it's a resource. The summary for policymakers has been launched. The full report will be launched in September, October. Sorry, I forgot that. I was going to check the date and I forgot. But what this integrated assessment is, it's very similar to ones that happened before for ozone and black carbon, for Southeast Asia, for Latin America. Now, this was a Pan-African assessment looking at different pathways forward for the continent in order to decrease both SLCPs and air pollutants. And so what there is per country is a harmonized approach that developed 3 different future scenarios. You can see those in the emission pathway here for PM 2.5, where you have baseline scenario, you have an SLCP mitigation, and then the really ambitious Agenda 2063. This is also the different pollutants that were looked at. And the LEAP model was used to develop these emission futures. LEAP is part of LEAP IBC. LEAP IBC is a reduced complexity model, but LEAP is an energy and emissions model for that. And so these exist, and these were analyzed for the whole continent, but also for different regions, and the data are available per country. And what's nice about this, because it was done harmonized, it can be used for regional assessments, for further assessments, but also it just has a lot of different detailed activity data. So this is an example of residential clean cooking, where we have now future scenarios. This is Pan-African, just to show an example, different fuel usage, of the different changes in emissions, and then also this break between urban households and rural households. So activity data are sometimes very difficult to find. And so now at least there's a harmonized approach, which now local researchers hopefully can take further and say, well, these assumptions were made X, Y, and Z. I know for my country, it's not true. And the model's available. So let's also improve on that. So I did just want to note that also the LEAP model will be made available. How to access it is explained in an article in the Clean Air Journal. When the full report in a few months is released, the model will be as well, both the Africa-wide model and the national model as well. And the hope is really, to work with researchers across the continent, as I said, to kind of downscale these results, because that's what, even in the release of the policy summary for policymakers, what policymakers were looking for. But I think this is a really good resource for even potential scenarios, which are hard to find. So just concluding thoughts, and then just 2 advertising slides. So yeah, I hope, I gave a bit of a whirlwind trip across parts of South Africa to show that, even with data scarcity, we do have some information, and we do very often have to use kind of innovative approaches, which particularly I haven't shown all of those, but, a lot of the assumptions we have to make in our mission inventory to move forward. And with policymakers, we've gotten good at communicating uncertainty of how to move forward with this. But it also highlights where the uncertainty is just too high to make a decision, but where we can still. In air quality management and in atmospheric science, the open and accessible data needs are large and wide-ranging as well, not just air quality atmospheric science data, but impacts and so on. We do have, I think, and I hope I've shown examples of how we have an interesting and complex atmospheric chemistry and air quality regimes from different sources, seasonalities, and trace gases that don't get a lot of focus right now. One question, as I noted earlier, and be interesting from this audience in particular, is how to really make strides in atmospheric chemistry with such data scarcity. And then we work very collaborative because we do have capacity constraints. There are experts here. We're smaller groups, so we don't have as many experts in everything. And just 2 quick advertisements. Sorry, I know time's going. As noted in the intro, I'm a member of ANGA, which sits under IGAC. If you'd like to join our working group or the mailing list, the website is here. And then also a lot of the research in Africa, some of it is getting published in the Clean Air Journal, which is a journal, peer-reviewed journal that's been around since the 1970s, focusing on air quality and atmospheric science in Africa as well. So you can visit our website. I'll just put that up again. I'd like to thank Wenfu and all the organizers for inviting me. And look forward to the discussion. Thanks.
Thank you, Dr. Garland, for a wonderful talk. If you have questions, please submit through, there's a button on beneath the screen, and if there's any questions, okay. Yeah, we'll be just okay. Since we'll be waiting for questions from audience, but I'll take the chance to ask the first questions, if that's okay. So you cover a lot of interesting topics. You talk about the spatial heterogeneity. You talk about local sensors and how it's challenging to to understand chemistry with some limited information. So my question is, like, from a measurement perspective, what kind of measurements do you think are really needed? First, like, we have a limited amount of resources. Should we put those resources in, for example, establishing low-cost sensors networks so that we have a good coverage and to know the spatial resolution? Or should we spend those resources to get more complicated research-grade instruments so that we can get more detailed chemical information?
Yeah, no, I mean, it's a good question and a difficult one. And I also think South Africa, my answer is probably a little different than it would be if I was outside of South Africa in another part of Africa, because we do have a regulatory network, and our regulatory network's not perfect, and the government's working on it, but we still do have stations, and we have stations that are working. And so I think for us, I think more strategic and more complex strategic measurements are needed. So for example, a few VOC measurements in key areas, I think would do a lot, and we just don't have those. Like that, even that starting to understand our VOC composition and also the reactivity. When we simulate ozone, we generally simulate it in too low of concentrations. And we wonder, is that because we just don't know anything about our VOCs? So I do think for South Africa, kind of key strategic, more long-term even, or long-term, little bit, more complex, even shorter term with specific questions is really what we need right now.
Thank you. We have a question from Winfrey from the audience. Hi, Rebecca, thank you for the great talk. Could you comment more on the low-cost models and how well do they compare to 3D models?
Yeah, so we're working on that right now. In the project that I showed, I didn't show the results, but as I noted with Carnegie Mellon and Peter Adams' group from there. And so for the US, they've had really good luck, not really good luck, they've had good skill with their low-cost models in comparison to CAMEX, for example. And we're trying to now do that here. So in some places, like South Africa, where we've run CTMs and we have some validation, comparing it here, but then also comparing it to models across the continent and trying to get to that question of how complex of a model do you need? Do you need to run CTM? So even if the low-cost model performance, perhaps the low-cost model, the RCM is a little bit poorer, can you still make robust decisions based upon it? So we haven't yet done the comparison of the Carnegie Mellon RCM to the CAMEX, for example, but in our GAINS project, the GAINS output and the CAMEX output look very similar. The GAINS is a much more complex reduced complexity model, and our local CTM, the CSIR CAMEX model, was used to develop those statistical relationships. So it's not as surprising that they did then have, they performed similarly.
Okay, thanks. Another question. Dear Rebecca, nice talk. Next IGAC meeting, will there be an Africa session? From Peter.
Thanks, Peter Nell. Thanks, Peter Nell. So I don't think that there will be a session specifically on Africa at the next, like in the conference, but we will most definitely have a side meeting for ANGA and discussions on that as well. So there will be the side meetings in IGAC, having an African session, and we're also trying to get more African-based scientists to IGAC as well. Very often there's not many of us that can travel for it. And so we're hoping to get more participants in Malaysia as well, so that maybe there won't be an Africa session, but maybe there'll be a lot more talks about Africa from African-based researchers.
Okay. Thank you. We're still waiting for more questions to come in. So besides the collaborations with Carnegie Mellon in the low-cost model, are there any ongoing collaborations with universities, organizations outside South Africa?
Yeah, a lot of our work we do in collaboration, both with researchers within South Africa, but also outside. And that's really, also, as I noted, we're a small group. And so we have expertise in certain things, but we generally, because we don't have a lot of data, we have data scarcity. And so we need to have different approaches. We need satellites and models and this and that. We generally don't have all of the expertise. So for example, the project with Traubomi currently, we have a couple of projects working with that data, and some are working with KNMI, and that we've made linkages through a workshop that we had in the Netherlands that Peter Nell was part of as well, but then also other researchers, to help with the expertise when in the areas where we just don't have people with that. So it's really key. But what we've noted with the collaborations, as we know, that a key aspect is that the research questions are locally led. And right, so it's what do we know are the research questions? I can have a long list of that, but what then, what we have our locally led questions, and then we come together on how to answer it.
Mhm. Okay, question from Shima. Hi, Rebecca, great talk. Would you please comment of different levels of stakeholders engagement that your team have had and elaborate on opportunities and challenges?
Yeah, no, thanks. That's a good question. And that can be a long discussion as well. So a lot of the stakeholders one of our main stakeholders is government, both at the national level and then very often at the city levels as well. We're very fortunate at the national level. We have an air quality officer where there's a lot of experts in air quality, a lot of people with PhDs actually in this field. And so we can talk the technical details with them. And then some of the larger cities also have well-staffed, really only a couple of the cities have well-staffed air quality networks. So some of the real challenges is outside of those areas, there's just not enough people focusing on air quality in the cities to be able to really, take forward a lot of this, because as I showed, a lot of the modeling is showing there needs to be changes across all of the different sectors in order to improve air quality. And I think they find the same thing in climate change as well, right? The transport department, they're focused on transport, they're focused on roads and on this, and they have enough challenges. And the same thing for health, health has all of these challenges, and now you're coming to me with something else that I have to think about and something else I have to add on. So one of the real challenges is getting outside of just the air quality office. The air quality office and us, we can hear each other, we can understand, but then it's the different sectors getting them on board. As well for, getting them on board for that. Then also with different stakeholders as well, there's a lot of grassroots action and there's a lot of NGO and action on that. And that's really focused often on industrial emissions. And industrial emissions, yes, our industries are polluting and they shouldn't pollute as much, but only focusing on industrial emissions is not going to get us to where we need to be. And so also those are sometimes challenging discussions as well, to talk about the different types of sources and how we have to look at across sectors really, not just industry. Because if you look at, like, for example, in the US after the Clean Air Act, it took decades for, in PM and ozone, some places still there is out of, not in compliance. It took a long time, and we don't really have that time right now, and we don't have tons of resources. So we need to make good decisions and effective decisions as well.
Okay, thanks for the answer. Have there been aircraft field campaigns in South Africa before for air quality? Are there any plans for that in the future?
Yeah, so in Southern Africa, there've been a few different field campaigns, aircraft campaigns. So Safari, the biggest one was Safari 2000, and that focused on biomass burning, but they did fly over land as well. And then, as I had in the slide, there were 3 big ones that focused on biomass burning. It's probably a long time ago. It's probably like 2017, but that was all over the coast. That didn't come onto the land. So it was the outflow of the biomass burning, really. The Northwest University group did use the South African Weather Service plane for a while to look at the vertical structure, for example, over the Highveld. But other than that, there currently aren't any plans currently, because there isn't, in South Africa currently, as far as I know, we don't have an aircraft for that. The Weather Service aircraft just hasn't been used in a long time. I don't think it's operational. So yeah, that's one of the things, particularly, thinking of this hotspot, we think a lot, we need measurements aloft, and it's not just composition, but it's also, we don't have many soundings. So when we try to simulate where the plume goes, and I didn't show that today, but if we simulate where the plume goes, different planetary boundary layer schemes within our model make the plume from the ESCOM power stations go in completely different directions. And we don't know which is right because we don't have the soundings, we don't have this vertical information. So there aren't any plans, but we're also trying to think, what type of remote sensing or even drone technology, that type of thing, to get some vertical information as well. But an aircraft campaign would be great.
Yeah, sure.
Yeah, right.
Okay, so maybe one last questions, and then maybe for the rest, Rebecca can answer them offline.
Sure.
Thanks, Rebecca, for a great talk. You mentioned a website with the air quality data. Could you put that up again?
Sure. Can I just answer in here? Or should I put on the if I put it here in Zoom? So it's SACWIS. So this is, yeah. Or do I put it on Slido?
Is it on your slide? So the talk is recorded, and we will post the talk to our ACOM YouTube page in the future soon. So maybe people can check there. Yeah, I think.
Yeah, I can.
Is
I
it
can
on
share
slide?
quickly. No, but I can paste it in to show. I have like this extra slides. So all of our data is on SACWIS. So I think you can see it here, sacwis.environment.gov.za. And if I show this, I think you can see it. This is our, so these are all of the data points. These are all the real-time and historical data that you can just download from any of the stations in South Africa. So it's SACWIS, South African Air Quality Information System.
Okay. All right. Thank you, Rebecca, again for this great talk, and thanks everyone for your time and attention and your questions. Yeah, have a good rest of your day. We'll see you next.
Thank you.
Thanks.
Cheers.